chapter 15 is about vector fields. So let's see what we can do with this. It starts in 15.1 is where we'll start, and we'll have a vector field of x's and y's. It'll look like this. It'll be m function of x's and y's, comma, n functions of x's and y's. This is a 2D vector field, as you can sort of tell, a two-dimensional vector field. And, you know, here I am just sort of talking abstractly, but there's my vector symbol. This is a vector field. Let's look at a specific one and see what we're talking about. If I just make up one, it looks maybe like this. I'm just making one up here. How about x, y, comma, 3x squared plus y. So I just made up this vector field. I have no idea if it's relevant to anything, but it's a vector field, which means what? Well, it means you can see it. What we do to plot a vector field, and this is very tedious, but what we do to plot a vector field is for every point in, what this is it's a function. And for every point in the xy plane, we can plug it in here and we get a vector. So let's just try like the point 0, 0. If you plug in the point 0, 0, you get the vector 0, 0. A picture of that is this dot right here. So let's move on. Let's go to, we can pick any point in the plane. Let's go to the point 1, 1. If you go to the point 1, 1 and plug it into this vector function, vector field function, then what you get is at the point 1, 1, you get the vector 1 times 1 is 1, comma, 3 plus 1 is 4. So you get the vector 1, 4. And so then at the point 1, 1, you draw the vector 1, 4, which goes over 1 and up 4. So there's a picture of this. Anyway, like I said, this can get quite tedious. I can do this for every point in the plane. Here, let's just try, what about negative 1, 1? Negative 1, 1. So that means x is negative 1, y is 1. I think I get negative 1, comma, 4 again. Negative 1, comma, 4. There you go. There's a picture of that guy. Well, I went up a little high. Should be the same as that guy. Yeah, again, a little tedious, but it's worth doing maybe a couple times to get used to what is a vector field. For every point in the plane, I can draw a vector. Let's just try one down here. Negative 1, negative 1. What happens at negative 1, negative 1? I get
3.
A 1 again, and a 3 plus, 3 minus 1, this time a 2. 1, 2. Yeah, 1, 2. So that's at this point, I go over 1 and up 2. Okay. All right, this is getting a little tedious. It's way tedious. I mean, it's awesome to maybe ask a computer, type in this vector field, and the computer draws it for you. You can do that with certain programs, certain calculators. There's probably some out there. You can probably access some cool app that'll do that. Type in the vector field, it draws the vector field. It plots every point in the plane and tries to draw a vector field for you. You know, this is the language of higher physics, and physics is things travel through a vector field. I mean, this is just some abstract mathematical vector field, and it didn't come out too great. But here's one. Except, maybe this is a 3D vector field. I was going to pretend this is the sun, and it's exerting a gravitational force on everything around it in 3D space. I can draw little vectors that represent the force field of gravity due to the sun. I think what would happen is in a certain radius around the sun, we'd have these large gravitational forces pulling us towards the sun. I think what happens the further away from the sun, I think we're still being drawn toward the sun, but maybe with a little bit less magnitude. Would you agree?
Yes.
A little less force. So look at me, I'm drawing shorter vectors. But I'm just, and by the way, this is sort of a 2D look at what's really happening in 3D. But again, further away, these vectors are still a little smaller, but still pointed toward the sun, the gravitational force of the sun. Put Jupiter in here, and all of a sudden you've got some, of course it's not really as big as the sun, but maybe then in places close to Jupiter, you've got a little distortion. You've got some stuff headed toward Jupiter, and not so much the sun. Or maybe something that's a little torn, whether it wants to go to Jupiter or the sun. So it kind of goes off in between. Anyway, now I'm really threw a kink into this, what was just a nice gravitational vector field. Now it gets kind of more complicated with two bodies there. But maybe you're getting the point. Let's see another example. Another example, they talk about a velocity vector field. They say if you're on a bicycle tire and you wanted to draw a velocity vector field, let's see if the tire's rolling this way, out on the edge you would have this velocity. What happens when you move closer? Oh, by the way, the velocity of this rotating wheel will be tangent to the wheel, I think. So these are velocity vector fields here. I think they're all the same speed out there on the edge of the tire. Whatever the speed of the tire is the speed of the vector, the length of the vector. But what about interior to the tire? What about halfway? Are you going slower? This point on the tire or on the spokes?
Omega R.
I think it goes a little slower, doesn't it? I mean, the radius is shorter. I think it's not going quite as fast. It doesn't have to, and right in here, I think it's maybe even a little shorter, a little slower movement. I'm drawing a velocity vector field of a rotating tire. And the further away from the center, the faster that linear velocity is. So it's represented by longer vectors. What was this? This was nothing. An abstract mathematical vector field. What was this? This was the gravitational force of a vector field of the sun. So there's real life vector fields in the world, mostly force fields, velocity fields, whatever can be represented by vectors, acceleration, but usually it's a force. It's force. It's some kind of force field. It could be gravitational force, could be frictional force, could be different forces. So it's cool to kind of see where they're used, but we like to just get into the math a little bit, get away from the physics sometimes. It just depends on what we're doing. So back to the math. Some of these vector fields are called conservative. Well, you know what? We've already studied vector fields, but we never knew it maybe. When I gave you a function like this, this was just a scalar function, and what we used to say, by the way, it's z equals, it's a surface in space, it's a paraboloid, to tell you the truth, what was that? Chapter 13 or so, I would ask to find the gradient. And the gradient technically was a vector field. Usually, maybe you didn't think of it like that. The gradient was a vector. It was the partial derivative with respect to x, 2x, comma, partial derivative with respect to y, 2y. I mean, that was the gradient. What we would often do back in chapter 13 was analyze this gradient at a point. So we would plug in a point and get a specific vector. What we never did was really, let's draw the entire gradient vector field for every point x, y in space. So we never did that, but that's kind of what I'm doing now. If I wanted to think of this gradient as a vector field, and if I wanted to plot every point in space, I could make myself at the point 1, 1, it's 2, 2. At the point 1, 0, it's 2, 0. At this point 0, 1, it's 0, 2. That's interesting. At this point negative 1, 1, negative 1, 1, it's negative 2, 2. Negative 2, 2. Wow. This is kind of interesting. There is some symmetry sometimes to these vector fields. That's interesting. Do you remember what the gradient did? What did it do?
Found the slope in any direction?
Kind of. It pointed to, in a way, the gradient wasn't a slope by itself. The magnitude of the gradient was the maximum slope.
Okay.
The gradient itself pointed in the direction of maximum slope. So if you're at this point, that's the direction of max slope. If you're at this point, there's the direction of max slope. There's the steepest direction on this surface. This is the steepest direction on this surface. So it's kind of interesting. So the gradient, which is a vector that points in the steepest direction of slope, is a vector field itself. The gradient can be a vector field. Again, we never would draw all the vectors. We would sort of analyze it at a point. We would draw one of these gradient vectors, usually at some point. But in general, at any point, it's a vector field. And when our vector field is a gradient, then he's kind of a special category of vector fields. So if a vector field can be interpreted as somebody's gradient, then that vector field is called a conservative vector field. So let's say F, the vector field F, is a conservative vector field. It is a conservative vector field, so that's one of the first definitions. Conservative vector field if this vector field F is somebody's gradient for some function f of xy. So if he's somebody's gradient, then he's called conservative. And, by the way, that function f of xy is called the potential function. Is called the potential function. So, that's kind of interesting. And, you know, not a coincidence that we use this word potential. Again, I'm not really a physics teacher, but this potential function is probably in physics, it's related to the idea of potential energy, or even the word electric potential, which is potential energy, which might be next semester's physics. But yeah, that word potential is not coincidental with physics, use of potential energy. And again, coming back to physics, I think it turns out that these gravitational vector fields, these gravitational force fields, I think they're conservative. But again, that's physics, this is math, they're totally related. But sometimes I like to approach this chapter, you know, kind of like it's, you know, sometimes we approach these topics very mathematically. So that's my mathematical definition of what it means for a vector field to be conservative. It has to be somebody's gradient for some function out there. That function happens to be called the potential function. To test to see if it's conservative, I'm going to say this. So this vector field, I'm going to just say this a different way maybe here. This vector field, which we refer to as M, like I did over there, comma, N, is conservative. I'm going to say this one more time a different way. This is conservative if the partial derivative with respect to M, the partial derivative of M with respect to Y is equal to the partial derivative of N with respect to X. That's kind of our test to see if a two-dimensional vector field is conservative. Yes?
Because ultimately, those are the second derivatives of the potential function, right?
Oh, maybe you're onto something. Hang on. Maybe you're onto something. Right. In general, what is a gradient? I mean, yeah, what is the gradient of some potential function? It is, like I just did it specifically, but it is the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y. You're right. And if I'm saying that the vector field is somebody's gradient, then you're saying that this m is already somebody's partial derivative with respect to x. And this n is somebody's derivative with respect to y. And then the test to see if it is conservative says to do his derivative with respect to y, dm dy, which is like doing his derivative with respect to y, which is like looking at this second mixed partial. You're right. And then this is like looking at his derivative with respect to x, which is like looking at his derivative with respect to x. Yeah, you're right. Essentially, you could restate that like this for some potential function f. Cool. It's kind of cool to realize that. Don't get lost in those layers, though. But it's important to think in those layers like that. Yeah, exactly. A vector field is a gradient if this is some fx and this is some fy for some f. And then the test is to do the second partials. That's interesting. To see if they're equal. That proves they're conservative. Let's just try one. If I just make one up here. F is this. 5x squared y minus 2 and 10xy plus 18. All right, is it conservative? Probably not. Is it conservative? Perhaps we should look at its voting record and who it's donated money to, which candidates. No, not that kind of conservative. Is it conservative? Let's see. What is dm dy? Dm dy would be the partial derivative with respect to y of m. This is m. If I do his derivative, that's just a 5x squared, right? And then if I do dn dx, that is dn dx is 10y. Anyway, they're not the same, so no. Not conservative. They're not equal.
Well, I mean, x squared equals, what, 2y?
Yeah, no, they're not equal. Cool. As we progress through this chapter, we'll learn reasons why it's important to discover whether is the vector field conservative or not. It helps me in my future endeavors here in this chapter. Is the vector field conservative or not? You know, the other thing, back to just basics here a second ago, we have this vector field f, m, n. That's a two-dimensional vector field. We can work in 3D. Of course, they're harder to draw and harder to work with. But just abstractly speaking, a 3D vector field would be a function of x's, y's, and z's, and it would usually, we refer to it as m of x's, y's, and z's, comma, n of x's, y's, and z's, and then finally p of x's, y's, and z's. And when it's a 3D vector field, then there's there's a couple of operations I can do on a vector field. I guess I can do them on a 2D vector field as well. It depends here. But here's a couple of operations in 15.1. I'll get back to this conservative idea in a minute. But here's a couple of operations. You can do what's called the divergence of f. It's called the divergence of f. Now here's what it is. It's the del operator dot product the vector field f. And we refer to this thing all by itself. This is called the del operator. I guess I used it to do the gradient. I erased all that stuff, kind of. But the del operator sort of acts on this function and does the gradient. But I've never really talked about it like it's its own operator before. I've had it in the context of this gradient. And here's what it is. The del operator is this. It's a vector. Notice it's a vector. And it's the vector that says, please do the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. Watch. It's this vector. d dx, comma, d dy, comma, d dz. But notice who is it d'ing? It's not d'ing anything. It's just this operator that says it's going to do the partial derivative of something with respect to x. It's going to do the partial derivative of something with respect to y. It's going to do the partial derivative of something with respect to z. But it's not doing the derivative of anything yet until it acts on something. So now this is going to dot product my vector field f, which I'm going to call m, n, and p. And so when you do a dot product, you know how that works. You multiply the x components, the y components, and z components and add them up. I use the word multiply, but what's funny is I'm multiplying d dx times m. What that turns into is I'm going to do the partial derivative of m with respect to x. That's d dx times m. I'm going to do the partial derivative of y with the partial derivative of n with respect to y. By the way, after I do that, I'm going to do the partial derivative of p with respect to z. When you do a dot product, you multiply those and then you add them up. And remember, this is not a vector. This is a scalar quantity. This divergence of f is a scalar quantity. Because remember, a dot product is a scalar. So this divergence is a scalar quantity. There it is. So what does it tell us? I don't know. It's a new kind of way of doing a derivative of a vector field. It's this derivative idea. I don't have a good meaning for this divergence. I don't really have a good meaning. There's some stuff I could read to you in the book and try to explain what it might mean. But it's a type of derivative. Here's another one. Watch this one. It's called the curl of f. Now the curl of f has a big vector symbol on it because it's a vector. Now why is it a vector? Because it's the del operator cross product the vector field f. And you know that when you cross product two vectors, the answer is a vector. So when you dot product this is a scalar. When you cross product, this answer is a vector. So, what does that mean? Well, it means I got to do this. I got to do a cross product. I got to do I, J, K. Who am I cross producting? The del operator, d dx, d dy, d dz, partial d dz, partial d dx, partial d dy, and I'm going to cross product it with f, which is capital M, N, P, functions of x, y, and z. And then I do this cross product, which results in a vector. And perhaps you remember, let's see, how would you do it? I don't know if I'll go ahead and do it. How do you do a cross product? You cross out i's column and row, and you do this little corner determinant here, which is dp dy minus dn dz, comma. Let's do the middle term. The middle term is the j term, which is dp dx minus dm dz. With, don't forget, when you do the cross product and you do this determinant, that j term has an automatic negative sign on it. Remember that? Comma, let's do the last term. The k term, you cross out k's column and you do this little minor determinant, dn dx minus dm dy. Wow. Listen, I don't memorize this, and I rarely write it all down like I just did. What I do, when someone says, go find the curl of a vector field, I go do this to a specific vector field instead of, I mean, I guess I could memorize this, and there's the answer, but I don't have this memorized, so I go do it. I go do the curl. I told you I didn't have a great meaning for what this divergence means. The curl is also hard to describe what it means, but I know a good use for it. One of the good uses for it is this. Hold on, let's go over here now. Hang on a second. What was the test? To see if a vector field is conservative, when it's a 2D vector field, this is the test. dm dy equals dn dx. Which, by the way, let's just notice something. If dm dy did equal dn dx, over here in this curl, if dm dy equaled dn dx, this would be 0. It turns out that that's the test for a 3D vector field. For a 3D vector field, this thing is conservative if the curl of f is 0. And that's 0 the vector, which means you do this curl and you get 0, 0, 0. If you get 0, 0, 0, the curl of f has helped you decide that this 3D vector field is conservative vector field. Cool. We just learned a lot of cool stuff about beginning vector fields. This is all kind of 15.1 stuff. Oh, I should practice some more. Now I should practice some stuff. I should practice some good stuff. So, how do you tell if a vector field is conservative? To me, you got two tests. It depends on if it's 2D or 3D. If it's 2D, it's this idea. If it's 3D, it's this idea. Which is kind of just an extension of this. Again, having this equal this, dm dy equal dn dx, is just sort of saying, yeah, this is a 0. But for a 3D vector field to be conservative, all three of these have to be 0. So I can memorize who has to equal who, but instead I just say the curl of f has to be 0. By the way, then, so I can just give you a vector field and say, is it conservative? And then you can do the test and say yes or no. So if it's not conservative, it's not conservative. If it's not conservative, then it's not a gradient. That means there is no potential function. If it is conservative, that means the vector field is a gradient. And that means there is some potential function out there. And so after you find out, yes, it is conservative, another good question then is, okay, then go find the potential function. Let's do a problem. So if I do a homework problem in 15.1, let's see what happens. Okay, this is really boring. You gotta check these directions. Okay, I'm gonna get rid of this stuff. Number 16 is kind of weird. It says, I'm in 15.1. I'm gonna do a little homework. It says, it gives me this function. Oh, but it's giving me a scalar function. X squared minus 1/4 y squared. They're giving me this scalar function, x squared minus, I thought there was, you know, this chapter is all about vector fields. This is not a vector field. This is some function. Maybe it's called a potential function. I don't know. Let me read what it says here. It says, find the conservative vector field for the potential function by finding its gradient. Oh, okay. Right. If I find this guy's gradient, which is an old chapter 13 thing, find his gradient. Okay. 2x, comma, 1/2 y. That's his gradient. It's the partial derivative with respect to x, comma, partial derivative with respect to y. Because he's a gradient, he is a conservative vector field. Okay, he is a conservative vector field. And, I mean, this is kind of, right. Usually we're trying to do this backwards. This is sort of forwards. They gave me the potential function. We found its gradient. That's a conservative vector field. And that's the potential function. Usually we're trying to do this backwards. They give me some vector field. They want to know if it's conservative or not. If it is conservative, then go find its potential function. Let's see. Let's try another homework problem. Okay, just for fun, let's try this one. 32. This looks kind of tough though. 32 is a vector field. It's just 2D. It's just 2D, I guess. And it is 1 over the square root of 1 plus xy in front of yixj. Wow. 1 over the square root of 1 plus xy in front of the vector y comma x. That was yi and xj. That's I write my vectors in this format like this. Yeah, that was it. Wow. What's the question? Is it conservative? Is it conservative? Well, how do I tell if it's conservative?
Some derivatives.
I need dm dy and dn dy. Here it is. If it's a 2D vector field, which it is, 2D vector field, I don't need the curl. I need just this, just dm dy and dn dx. That's going to take a little work, man. See, what is my m? What the hell? My m is y over the square root of 1 plus xy, right? I kind of got to distribute this back in to see my m. What is my n? My n is x over the square root of 1 plus xy. Well, great. If I'm going to do these partial derivatives, I guess I got to do quotient rules or something. Who picked this problem? Let me try this. dm dy. Yeah, I guess I'm doing a quotient rule. Derivative of the top, 1. Right down the bottom. Minus. Right down the top. Take the derivative of the bottom, 1/2. 1 plus xy to the negative 1/2 times the derivative inside, with respect to y, the derivative inside would be an x, all over the bottom square. Well, I might need to work on cleaning that up.
Looks like you might be able to pull out square root of 1 plus xy.
I know. I used to
Simplify
do
some.
that back in my Cal 1 days. I would pull out 1 plus xy to the negative 1/2 out of this, and I would work on cleaning it up. You know, I'm going to skip that for a second. I'm going to jump to the dn dx. Let's try the dn dx, which is almost the same thing. See, there's a lot of symmetry in these sometimes. Anyway, here we go. Derivative of the top with respect to x is a 1. Right down the bottom, minus, write down the top and take the derivative of the bottom, 1/2, 1 plus xy to the negative 1/2, and then the derivative inside there with respect to x spits out a y all over the bottom squared. Again, you know what? Without any simplifying, these are the same. I can tell they're the same. Look at them. So I didn't waste any time simplifying. I could see some patterns coming. So this dm dy is equal to dn dx. So yes, f is conservative. If that's all they wanted, that's all they wanted. Yes, f is conservative. But it's because of this. It's because dm dy equals dn dx. Cool. Let's do another one. All right, you ready? Here we go. 34. I'm in 15-1, doing some homework. Oh, I'm making progress today. I'm making progress. 34. And the homework says, different little set of instructions. This time they give me this vector field f. It's 2D. Determine whether it's conservative. If it is, find the potential function. Okay, that's good stuff. This is good stuff right here. 3x squared y squared, 2x cubed y. So my vector field is 3x squared y squared, comma, 2x cubed y. Again, they write their ij components. I kind of write it like this, but that's equivalent. And then anyway, how do I test to see if it's conservative? I do dm dy, and I do dn dx, and I hope to see if they're equal. Let's see what happens. What is dm dy? 6
cubed y.
x squared y.
Right.
And then what's dn dx? 6 x squared y. Okay, then yes, it's conservative. So now, find the potential function. Okay. This is good practice. This is good exercises for us. We'll need this. All right, so we were talking about this earlier. So we said, okay, so that means he's conservative, which means he is somebody's gradient, which means this is already, I know I called it m, but it is fx is what it is. And if I'm trying to get back to f, perhaps I should, if this is the partial derivative with respect to x, and I'm trying to get back to f, perhaps I should integrate with respect to x. That'll take me back to f. I should. That's what I should do. I should integrate 3x squared y squared with respect to x. That'll take me back to f. But hold on. This is fy. This is the partial derivative of somebody with respect to y. So I want to find that somebody. I think I should integrate this with respect to y. Okay. I'm going to integrate this with respect to y. Now the thing is, I think when we do this, we should get the same answer maybe. And we'll see. They might be some different. We'll see what happens on this one. Let's try it. Here we go. I'm trying to get back to f. I need to integrate with respect to x. This is very logical. Here we go. With respect to x, you get an x cubed. You divide by 3, cancels the 3. I think you get x cubed y squared, right?
Yeah.
Okay, hold on. Plus some constant. Now wait a minute. Who was the variable of this integration? The variable of this integration was x. So who did we just treat like a constant?
Y.
Y. So when we spit out this plus c, it isn't necessarily a hard constant. It could be a function of y's. Because we just treated y like a constant. It won't have any x's in it. The x's are variables. It won't have any x's in it. But this constant could have y's in it. I don't think it will on this problem. Watch. Let's integrate this one with respect to y. Integrate with respect to y. Y squared, divide by 2 kills the 2. I get x cubed y squared. Plus some constant, but that constant could be a function of x's. So now I stare at these two things, and I sort of, my final answer is this f, which is that f, or a combination of those f's. I mean, the potential function is this function we just discovered. And this is not the best example, but sometimes you have to kind of figure out what do you need here? Well, I mean, look, if this is f and this is f, well, okay, they have this in common. I think that should be in my final answer, this x cubed y squared. But you know, this says that this could have some constants that have y's in them. Well, there's nobody down there that matches that. There's no, see, this matched this. So check it off, put it in the basket. Do we see any y's that would, there is no y's that really match this, and there's no x's up here that match this. So there's nothing that there's nothing here that matches him. There's nothing here that matches him. The only thing that could match is if there was no y's and this was just a constant, and this was no x's and just a constant, then they both could have a constant. Let's put a constant in here, and that constant we call k. That's the potential function. I'm sorry if my explanation got weird there. We need him, and sometimes we have to try to match this up. There was nothing to match this up with, so only thing we got out of it was a constant k. We were presented with a vector field. We tested it. It was a conservative vector field, which meant he was the gradient of somebody, some potential function. Please find the potential function. We did. You have to integrate to get back to the potential function. Let's do this again. Let's keep doing homework here. I want to do this with a 3D. Let's do this with 3D here. Boy, those are tough examples there all of a sudden. Hang on, damn it. Yeah, okay. All right. I don't really like their examples. I think I'm going to make up my own example. So do not look. Okay, don't look. Don't look, don't look, don't look, don't look. Don't look, don't look, don't look, don't look. Wow, dude. Look at that. That's a 3D vector field. It's a nasty one too. What's the question? It's a 3D vector field. What's the question? I think the question is it conservative? Oh shit, how do you tell if it's conservative?
Curl.
You gotta do the curl. Oh my goodness. Okay, I ain't scared. Here we go. I ain't scared. I gotta do the curl. How the hell do I do a curl? I gotta do the curl of F. The curl of F is the cross product of the del operator. So I need my I, J, K here. They're kind of just placeholders. My del operator here, ddx, ddy, ddz. See, my del operator is treated like a vector itself, and then it is cross-producted with the actual vector field, which is here. 10xy plus 2y e to the xy plus 5 cosine x. Wow, sorry about that. What's this? 5x squared minus 2x e to the xy plus 2yz. I'm going to move this over. And then my k is y squared. That's interesting. There's my vector field. Bam, bam, bam. There's my ddx, ddy, dzz. I got to do this cross product. Oh, wait, what am I supposed to get? Oh, I'm supposed to get 0, 0, 0. And that, well, if it's conservative, I'll get 0, 0, 0. Well, let's see what happens. Let's see, how do I do the cross product? I do the partial derivative of this with, I remember I cross out i's column, and I do the partial derivative of this with respect to y. That's pretty easy. 2y. Minus the partial derivative of this with respect to z. The partial derivative with respect to z, what is that?
2y.
Sure is. Well, so far so good. We got a 0. Who's next? There's a negative in front of the next one. The next one is, we're crossing out the middle column now. We're doing the partial derivative of this with respect to x. With respect to x, the partial derivative is 0. Minus, then we're doing the partial derivative of this with respect to z. And there ain't no z's in there, so that's a 0. Wow, so far so good. Finally, I'm doing, I'm crossing out k, and I'm doing this partial derivative with respect to x. Okay, partial derivative with respect to x. Holy shit. All right. That's a 10x. Oh my God, I got to do a product rule. Derivative of the first
2
times the second minus the plus the first times the derivative of the second. With respect to x, it spits out a y minus this derivative with respect to y. Let's try it. With respect to y, this derivative is 10x. And with respect to y, this is a little product rule. This is nothing. This is a little product rule. It's the derivative of the first.
Negative 2e to the x1. Or maybe not negative.
He was negative. I wrote it down wrong. He was negative. Good. He needs to be. Negative 2 e to the xy times minus of 2y e to the xy times x. I swear to God, that's a 0. It's the same thing. This thing minus this thing. Whew. It's conservative. That's a lot of work. But I just proved that the curl of f for this particular problem was 0. By the way, that means 0, 0, 0 is what that means. So, awesome. So this guy is conservative. All right, so now he's conservative. So what? So he is the gradient of some potential function, is what he is. He's a vector field in his own right, but it can be written as the gradient vector field of some potential function. Can we find that potential function? Well, we got to work backwards. This is the fun part. In order to find this guy's potential function, I think this is this is fx, this is fy, and this is fz, and we got to try to get back to f. So we have to integrate with respect to these variables. So I have to get to f, I have to integrate this thing with respect to x. I also have to integrate this next thing with respect to y. And I also have to integrate that last thing with respect to z. Now, watch this. Let's do this, okay? I'm sorry there's a lot of writing here. But let's do this, and I'll tell you what, let's start with the last one. Can you integrate with respect to z?
zy squared.
Okay, y squared times z, plus some constant. Now, what will be in your constant? Well,
X's and Y's.
yes, you just integrated with respect to z. The variable was z. The x's and y's were treated like constants. So this constant, that's normally just a plus c constant, could have x's and y's in it. All right, now what I'm trying to do is, technically that's f, but I'm trying to match it up with these other versions of f that I find by integrating these other terms. So let's work on it. We'll go to the top. I'll go to the top now. Integrate with respect to x. Integrate with respect to x. Treat y as a constant. So x squared over 2, 5x squared y. Integrate with respect to x, so that's a constant. So you're integrating e to the xy. Isn't that just e to the xy? What does
No,
it do? You
times
spit out
times
a,
y.
you spit out a 1 over y when you integrate.
Ah,
I
okay.
think you spit out a 1 over y, which cancels this y. I think I get negative 2 e to the xy.
Yeah, because you'd have to use substitute.
I do a little, I'm integrating, I do a little u substitution, spits out a 1 over y, kills that y, I'm happy. Now I'm integrating this, a 5 cos x.
5 sin x.
I think it's 5 sin x. Awesome. With respect to x, I just integrated with respect to x. So I treated the y's like they were constants, and then there was no z's there, but I also treated, so this constant out here could be a function of y's and z's. X was the variable, the constant it produces could have y's and z's in it. Let's do this middle one here. Integrate with respect to y this time. With respect to y, 5x squared y. With respect to y, you get e to the xy. It spits out a 1 over x. It kills that x. I think you get negative 2 e to the xy. Integrate with respect to y squared
z.
over 2. The 2's cancel. Y squared z. Plus some constant that might have
X's and z's.
x's and z's in it. So, there's f. F is staring right at you. What it is it's some combination of those 3 f's there. The ultimate f, the potential function, f of x, y, and z, is just made up of these 3 dudes. Now I like to kind of watch it match up. Like let me see. What do all 3 of these have in common? Well,
Nothing.
now wait a minute. Here's how I'm going to talk kind of funny. Watch. All right. Here's something that this one has in common. This one has it in common. And then you look down here and you think, well, this doesn't have it. Or does it? This constant function of x's and y's is what matches up with these x's and y's. These are all just x's and y's. So that matches with that, which I'm going to claim it matches with that. Therefore, I need it in my answer. 5x squared y minus 2 e to the xy. Yep, that all needs to be over there. Let's see, what else do they have in common? Oh, look at this. They have the y squared z. This one has the y squared z. Oh crap, this one doesn't. Or does it? Right? That's my y's and z's. That's a function of y's and z's. I can say that that matches these y's and z's here. So I need that y squared z in my problem. What else? Oh, it's got this, function of x. Well, okay, in a way that, well, I could say this is a function of x, couldn't I? It just doesn't have any z's. It doesn't have to have z's. So I could say these match up. And I might say I've already used this, but if it's a function of x, it could be used here, right?
Yeah.
So I need him to. The truth is, you don't really have to sit there and struggle and line all this up. The truth is, anybody that's here, it is fun to try to match it up, but anybody that's here needs to be there.
Plus a k.
Plus a k. And don't write things twice. These things match up. It only gets written once. But plus some k. You're right. We did it. Wow. That's kind of tough work. What was tough was at the beginning, just to test to see if it's conservative, I had to do that curl, which was kind of a job. But then once we found out it was conservative, I had to integrate each one of these to get the potential function. This was a good one. The ones in your book were a little easier. I made up kind of a better one here. Yes?
By the way, it's going to go over.
Oh, yeah. Good. I think I'm about done anyway.